So this table summarizes the differential rules, and you notice that the language we are speaking now, differential derivatives, comes from the word differentiation. All right. Rules for a polynomial. A polynomial has that general structure. There's a constant, a coefficient. You have the variable raised to a certain power. All right. The power are normally integers. Okay. So they call that polynomials, where n is equal to a whole number, right? Because you have negative integers, a whole number. Okay. But you can have negative powers. And you can also have fractions too. So that general form, if you want to put it, ax to the n. So whenever you have a situation or a function or an equation, and it is of the form ax to the n, then you can apply this rule now to differentiate it. Okay, so dy dx or y prime or f prime of x is equal to ne. So you take the power, you multiply it to the coefficient, and you subtract one from the power. Okay, here you've got two of them, and that's the sum. So they call that the sum rule. I don't really want to write it as a rule, but the differentials of the sum is the sum of the differentials. So because you have a 5x cubed and a negative 3x squared, you can distribute this rule to each one of them. Okay, so you can apply the differential rules to the 5x cubed and to the negative 3x squared because of the sum that is going on there. Remember, this is 5x cubed and minus 3x squared. Okay, so here you have it. The 3 is multiplied to the 5, that's like what the rule says, and you subtract 1 from the power. And the 2 is multiplied to the negative 3, and 1 and 2, subtract 1 from 2 will give you 1, and you get 3 5s are 15x squared minus 6x. So this now is called the gradient function. The gradient is equal to 15x squared minus 6x. So you can use this equation to find the gradient at any point on this curve. Okay, this is what is actually going on here. You may have an equation like y is equal to 12x. The rule says it's the same, this is the same rule, but it's a specific situation. You're still applying nax to the n minus 1, but here now n is 1, okay, and then 1 minus 1 is 0, x to the 0 is 1, 1 times a is a, so you are just left with a. Okay, so anytime you see your exponent is 1, you can just write the coefficient as the gradient. Okay, and it makes sense because this is y is equal to mx. M is the gradient is 12. If you just have x by itself, meaning 1x to the 1, the gradient will be 1 because there's an invisible 1, which is the particular value of e. So when a is 1, a is 1 will be the gradient. So y is equal to x, a is 1, the gradient is equal to 1. Okay. Now, if you have a letter or a number by itself, for example, f of x equals 7, the graph of a constant is a horizontal line. A horizontal line does not have any y change. Y doesn't change. Y is equal to 7. That's what it says. Y is equal to 7. So no matter what happened to x, y is 7. Y doesn't change. Okay, so therefore the gradient is 0. Because bear in mind the gradient reflecting how the y changes. You see that gradient of 12? That gradient of 12 means that the y changing by 12 when x changes by 1. All right, that's what the 12 means, you know. When x changes by 1, the y changes by 12. All right, always bear that in mind, the definition of gradient. When x changes by 1, the y changes by 1. When x changes by 1, the y changes by 0. A horizontal line has no y change. So that's why, you know, the gradient of a constant is 0. Here you have an example, y is equal to x cubed, 8x cubed plus 3x squared plus x plus 6. So all this is sum. You have 8x cubed and a plus 3x squared and an x and a 16. So you can apply that rule for each one of them because this is a sum function. A sum function meaning the terms are being summed. All right, each term has a variable, and the variable now is by itself, which is x. Okay, so therefore now this rule can be applied to each term separately and then added. So we're going to apply it to the 8x cubed. So here we multiply 3 to 8 and we subtract 1 from 3. Multiply 2 to 3, subtract 1 from 2. Multiply 1 to 1, subtract 1 from 1. And here x turns to 1. A constant has no y change, okay? But also you have x to the 0 there, you know. There's an invisible x to the 0 because 1 can also be written as x to the 0. Okay, so if you have x to the 0, you can also prove it also. 0 times 16 is 0, applying the rule. Okay, so this confirms that is 0 another way. All right, apart from saying there is no y change because you have a horizontal line, you can also say x to the 0 means 0 times 16. Okay, and then anytime you see multiply any number by 0 is 0. And here you have it. This is the gradient function for this curve. So you can use that gradient function to find the gradient at any point on this curve. Okay. Example 2, find the gradient of the tangent of the curve. Y is equal to 2 over 3x cubed plus a half x squared minus 5x minus 9 at x is equal to 2. So here now, after you have differentiated, applying this rule, you have the gradient function. Here it is. You can calculate the gradient at any point on the curve. So here the question says, what is the gradient when x is equal to 2? The gradient is 5. The gradient is equal to 5 because you substitute 2 into the gradient function to get the gradient at that point x equal to 2. So very importantly, always try to interpret or always try to have in memory the definition of the gradient. With every unit change of x, that's what the 5 means, you know, that's what the gradient of 5 means. Every time x changes by 1, the dependent variable y changes by 5. So it is going up by 5. Every time x changes by 1, that's what gradient means here. Okay, so these are 2 examples of the application of the differential rules for any function that has that format, ax to the n. And also, when each term is being summed, then this rule can be applied to each term. All right. Summed also mean a negative between them, as you can see. Okay.